Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can quickly solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve one problem, but how to teach themselves a solution to an unfamiliar problem. For now, I am learning Python. I have no professional experience or formal training in the language, and have only been learning it since mid-January. While I'm picking it up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 15th Project Euler problem, talking through my thought process as we go. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Problem 15, Lattice Paths. Starting in the top left corner of a 2x2 grid and only being able to move to the right and down, there are exactly 6 routes to the bottom right corner. How many such routes are there through a 20x20 grid? So, full disclosure, spent quite some time on this yesterday. Did not really get anywhere, but trying again today, and I've thought of sort of a new approach to using recursion. So let me pull up the code. Okay, so here's everything that I did yesterday. We're actually going to keep this part. We're going to ignore all of this noise. I don't want to care about this. So this is all notes of trying to think through the problem, because the first step to solving any problem is making sure you'll really thoroughly understand it. And I think, honestly, that I was overthinking things. I was trying to find the pattern. I was trying to figure out a formula based on the pattern. I tried simple counting with multiplication and addition. I tried making a recursive function, but I think that I made my recursive function too complicated. So I am going to ignore my num roots thing, and I'm actually going to comment out this print and all of this. So instead of doing all the things that I was doing here, which was like trying to go through it systematically, counting the various paths based on various rules that I'd seen kind of repeating in my search. But honestly, I think the real key to this is literally just if we hit a limit, that's one route. So in this case, right, let's go back to the 2x2. I'm going to change my limit back to 2. So we start with 0, 0. Now I'll pull up the picture. We start with 0, 0. Then we look at both 1, 0, which is this point, and 0, 1, which is this point. Both of those, you have 2 different options that you can take. You can go to the right or down. So this point is going to be 2, 0. 2, 0, limit, there's only one option from there. So based on that, it's kind of like how many paths to the edge, or to the opposite edge, either one. So I'm going to effectively, let's just comment out all of this. and write new code at the top. So I'm kind of not going through all of this old code because it didn't work. But let's see if we can get my new idea working for just the simple case of a 2x2. So here, what we want to do is if x is equal to the limit, or y is equal to the limit, return 1. We found a path. Otherwise, return same function, but we go 1 to the right and 1 down. So I think actually I am going to bring this back to the print. If I am correct about how this is going to work, we will end up traversing certain points multiple times. But it should theoretically still give us that value of 6 that is the correct answer. So let's go ahead and run this. Okay, so we did get the correct answer here. Let's go ahead and run it with a limit of 3. So I spent a lot of time yesterday trying to figure out the correct answer for 3. I kept coming up with different numbers. I think at one point I found it to be 19, another point I found it to be 26. I should just kind of draw this out instead of trying to count visually. But let's see what answer this program gives us for the number 3. This time we get 20. I don't think that is correct. But I'm going to go ahead and try with that limit of 20. I'm going to comment out all these lines that are printing every single coordinate. Actually, let's look here. Are we hitting certain coordinates more than once? So like 1, 0, sure. 2, 1. Does 2, 1 show up elsewhere? It does. So that's a good sign because it means we're hitting it more than one time. Yeah, let's just see what we end up with for 20 by 20. Obviously, it's taking a bit longer. Probably because counting to 20 is just significantly larger than counting to 3, and it's going through all of these points like systematically, hopefully. And just I did not do any sort of seeing how long it took in between. So let's let this run a little bit and I'll talk through my thought process here. So basically all this function is doing is it's saying, have we hit the wall? Can we go either no more to the right or no more down? Okay, that's one path. If we can't eliminate it to just the one path, then we call the function again, incrementing x by 1, and again incrementing y by 1. So for the 2 by 2 case, we did see that it worked. Not sure about the 3 by 3 case, obviously not sure about the 20 by 20 case. But like, if you see here, so let's manually look through it for like 2 by 2. We're calling it with 0, 0. So we always start in that upper left. Come in, 0 is not equal to 2, so neither of these work. So then we call count routes with, let's just focus on this first one. 0 plus 1, 0. So again, not the limit. Call it with 2, 0. 2 is the limit. Return 1. And then we're calling it with 0, or let's see, 1, 1. Neither of those are the limit, so we call it with 2, 1, and 1, 2. Both of those are the limit, so that's a 2. And obviously this gets pretty complex pretty quickly. And also, obviously, we've been going for a couple of minutes here, and this function is spinning and spinning and spinning. It's not giving us any answer yet. I don't know how long it will take. This is the first time writing this. I honestly haven't done recursion in a while. But we saw it work for 2 by 2. I don't think it worked for the 3 by 3. Let's see. So I pulled up this 3 by 3 grid. And let's say this corner, that's 1. This corner, we already did the only route to the right, so thinking down. Let's preference the right, so that's 1. Down again, preferencing the right, that's 2. Down again, preferencing the right. Well, we can't really. So that is a total of 4 routes. Come to here, go down. And here, again, we notice that we've hit a 2 by 2 grid. So we know the answer there is 6 from here. And then again, from here, if we prefer the right, answer's 6 again. So we've got 4 plus 6, which is 10, plus 6. Come down here. That's 1, that's 2, that's 3. And that's 4. So it looks like 20 is the correct answer for the 3 by 3. And I'm kind of trying to see here what is the pattern still. Because obviously this is taking so long to run, it cannot be the correct answer so far as like meeting the efficiency requirements that Project Euler is encouraging. I do want to let it continue to run because I want to know, does this give us the correct answer? Based on the most recent count that we just did, I think yesterday I was starting to get kind of tired and starting to overcomplicate things. And I just got kind of lost in the weeds. I think 20 is the correct answer for the 3 by 3. So I do think it will give us the correct answer for the 20 by 20. It's just not doing it efficiently. So I'm actually going to go ahead and delete some of my commented out code here. So all of this, ignore all that. Okay. I'll leave that one for right now. Here, I was just kind of trying to count through them and see if I could add or subtract. Here, obviously, I was trying to go through and find the pattern. I think the pattern is a lot simpler than I was thinking. So, let's see. So for here, we get 1. For here we get 1. For starting here, we get 3. 1, 2, 3. Starting here, we get 6. Starting here, we get 6. Starting here, we get another 3. And then starting here, we get 1. So this case, it's 1 from each of these corners. And then from here, it is the number of squares in a column or a row. And then from here and from here, it's the number of squares in a grid one size smaller. So let's try to use that thought to think of how big a 4x4 should be, or how many of these routes should exist in a 4x4. So if we say 1 plus 4 plus 20 plus 20 plus 4 plus 1. That might not be the correct answer. Let's go ahead and look at a 4x4 grid and see. Okay, so 1, 1. And one thing to note for sure is that these are symmetrical, always. I mean, obviously they're symmetrical in all directions because it's the square. Well, okay, all of the diagonal, up, down, left, right. So there's going to be 1 num columns. Then you get to here and it becomes complex. Obviously, when we come down here, we know we're at a 2x2 grid. But what about when we come down to just here? There's 1. And there is 3. So let's make some notes. And maybe I'm overthinking it again. We shall see. So for the 1x2, or sorry, for the 2x2, it's 1, 1, 2, 2, so it's 1 plus 2 plus 2 plus 1. That's the actual for reals formula that comes up to the correct answer. And then for the 3x3, it's 1 plus 3 plus the 2x2 plus the 2x2 plus 3 plus 1. And then for the 4x4, if we didn't think about the pattern too deeply, it would be like 1 plus 4 plus 3x3 plus 3x3 plus 4 plus 1, which is exactly what I originally said, but that's not correct because it is ignoring coming to this point and going down. So here it's going to count the rows as if from a 2x3. And that's a little bit trickier, isn't it? Because well, let's just kind of count it and see. So obviously here's 1, come here, and then there's 3 different possible routes. If we go down, then there's another 6. So 1 plus 3 plus 6. And of course it'll be the same for a 3x2 as for a 2x3. So what's the formula here? It's going to be 1 plus 3 plus 2x2. And obviously this is both directions. So we're starting to see, like, here it is. So this, even obviously in IntelliJ Visual Studio Code is helping us here. Also, I just want to note it's been over 12 minutes. This formula, this has still not finished. And what we notice here is this is half of a 3x3. So let's guess at the formula for a 5x5 and then check ourselves. So it'll be 1 plus 4 plus or 1 plus 5 rather. And actually, let's simplify our terms here a little bit. This is 1/2 3x3 which actually, if you look at it, it ends up being 3 of the 3x3, which is interesting and maybe helpful. So then, again, just to simplify our terms here, not where I wanted that. And again, we're missing this, like, sort of in-between state. And I think what it is going to end up being is 1/2 3x3. Let's check ourselves. So this would be going all the way to the right, going on all but one way, all the way but one to the right, all the way but 2 to the right, only 1 to the right. Hold on. All the way, all minus 1, so 4 to the right, 3 to the right, 2 to the right, and then this is just 1 to the right. And then obviously this is symmetrical, as we saw. So let's see if that formula that we've just come up with kind of stays for the 5x5. Okay, so the ones we know. The corner's always going to be 1. The, like, all but 1, always going to be the same as our limit. Because 1, 2, 3, 4, 5. And we know that here we're going to get to the 4x4. Here we're going to get to here, which is Maybe not half the 4x4, actually. No, it would be. It would still be half the 4x4. I think. Let's see. So obviously 1, 4. 3, or sorry, 1, 3, and then 6. So 4 plus 4 plus 1 plus 6. 4 plus 6 is 10, plus 4 plus 1 is 15. So maybe not half. Well, yeah, again, like, I'm starting to, like, get a little bit confused, and I'm sure this isn't easy to visualize for most of us. But I do think this is it. So let's try to generalize this. So let's say 2 times all of this, because that's what it really is it's 2 times. So it's I plus n plus 1/2 n minus 1 plus 1/2 n minus 2 to I don't think it'll ever get down to the, like, 2x2. So how do I express this formulaically? Okay, so let's ignore the case of the 2x2 and the 3x3 for purposes of the formula, because they're a little bit special. And instead of n minus 1 here, let's say 3x3, then 4x4, 2 n minus 1 by n minus 1. And then we would want to do plus n minus 1 by n minus 1. I think that that's our formula. Let's go ahead and see if we can program that formula. Alright, so let's just kind of type it out. Num roots equals 0, 4, and actually roots per limit, or limit to roots. I'm going to go ahead and initialize this with the 2x2 and the 3x3. So for 2 it's 6, and for 3 it's 20. And then we want to go for I and let's say range limit plus 1, and I want to start at 1. Okay, so corners is always 2, or let's think about it this way. Let's see, so yeah, we basically just do let's see, so starting with number 1, it would be 1 plus 1 because there's only those 2 corners, right? So for j in range one I plus 1. And what it'll do is it'll kind of start to give us this inside part, I think. Actually, maybe we should start with I and count down. Not sure if we want it to be a 0 or -1, honestly. Well, let's just kind of see how we do. So, if j, we don't need these parentheses, if j equals I, then we want to say num routes plus equals. I'm going to explicitly call out that this is 2 times 1. Obviously, I could just write the number 2, but I think we want to be more clear. Okay. So otherwise j is going to be less than 1, or less than I, to kind of represent that, like, this corner. So else if I minus j equals 1, num roots plus equals 2 times I. Else. So then we would get to the case where we're looking to see if, like, so we've got our 1, we've got our n, Now we're kind of looking at this half plus half of 3 by 3 scenario, so this would be I minus j equals 2. So we don't really want to make this a string case, or like a switch case, I mean. We kind of want to formulaic it and not just manually type out all of these things. Else size equals I minus j. And what we want to do okay, so let's say else if I minus j kind of trying to think through this part. So else if I greater than 3 and I minus j greater than or equal to 3 and I minus j less than or equal to I minus 1. I am going to rename this variable because it is confusing me to have it like okay, that did not do what I wanted. Rename. Okay. Let's rename this j to I. Okay, so now we're looking at n instead of I and j. So we know like our n is a substitute for our limit. It's the n in our formula. Okay. So now size, and we're actually going to add num routes plus equal limit to routes of size. And let's go ahead and ignore inlineness instead of having it be a variable. Now, why did I just do that? Because it is technically 2 times 1/2 equals 1. So we are currently counting this part of the formula. And what we want to do is basically, while we're counting that part of the formula, it's all the half of these grid sizes, but then we're going to multiply those by 2 to cover the other diagonal. And of course, like, that's not gonna work super well. Okay, so now at this point, when I is equal to 1 should be the only time when we get to this point. So I'm just going to write else, and we'll correct it if that ends up not being right. Num routes plus equals limit 2 routes. And this one we are going to do the 2 times of n minus 1. So in this case, I should be equal to 1. So this, let's make ourselves a little note, because sometimes that's helpful. Okay, so we've gone through this for loop. Let's kind of think about this for like just a limit of 2. So n equals 1 for starting. So I in range in 0, so we've got 1, 0, so this I will only execute once. N minus I is 1, so we'll be doing 2 times n is 1, that's 2. And then that's it for that part of the for loop, and then n becomes 2. Come in for I in range 2, 1. We get 2. So I equals n is 2 times 1. Okay, I may have confused myself here. So if the limit is 2, then I starts out as 2. N starts as 1. So we come in here, I is 1, n is 1, so I equals n num routes plus equals the 2 times 1 to represent those 2 corners. So num routes is now 2. For 2 in range 1, 3. For I in range 2, 0, so the I will run twice. Once for 2. Again, we're getting the 2, 2. Or the 2. So now our num routes is 4. But then we come into here with I of 1, and n minus 1 equals 1. So 2 times n is 4. Okay, so this sort of range thing, we're going to want to reset num routes. Do we really need to have it be this intense? We could just say for I in range limit 0, I think. This is really our thing. Here's the issue, is we want to build out this array. And we want to do so programmatically. So here, we are not going to set num routes back to 0 yet. Limit to routes of size n equals our num routes. And then num routes actually feels a little bit cleaner to just have this line right here. Now, for 2 and for 3, it should not be going in all of here. Okay. So let's do some prints here just to like see our code working. Time check on the previous run. Oof. Over half an hour, still not done. Obviously not gonna work for us. And I just want to print out, because what we should see for our... Let me just yoink. I want to keep these notes here. I might want to go delete those other notes. I might leave them just to show some thinking. But... Okay, so what we should see is print inside n minus 1 equals 1. Or n minus I equals 1. Finding num roots for n by n grid. And then here I'm just going to print and this needs to have an F on the front of it, I think. Okay, so for starting with the number 1, we expect it to find 2. We expect it to only go inside of here. For the number 2, we expect it to go inside of here and then here. For the number 3, we expect it to go inside of here and here and here. Okay, so let's say print inside inside the half grids part, else print Okay, so the first time that we should get here is for n equal to 3. I'm going to go ahead and put this limit down to 5. I'm going to go ahead and comment out this part. It did not seem to work the way that I wanted. And then we're just going to print limit to roots of limit. See how well that works for us. So again, I've set our limit to 5. We don't actually know the correct answer for 5, and I personally, at least, have not done the math for the correct answer to 4 either. But I just kind of want to see this work. And I'm also going to go ahead and print our limit to roots list, or dictionary, entirely. Yikes. I think that got into an infinite loop, perhaps? Not quite sure how. Let's run our new one. Okay. So, finding num roots for a 1 by 1 grid, found 2 roots. That is correct. found num roots for a 2 by 2 grid inside n equals 1, inside n minus 1 equals 1, found 6 roots. That is correct. 3 by 3, we went inside the 1 equals n, we went inside the n minus 1 equals 1, we went inside the n minus 1 grid lookup. That's exactly what we expected. We found 20 routes. That's the correct answer. For 4 by 4 grid, we went inside the I equals n minus 1, n minus 1 grid lookup, which is not how I expected that to go. And then we went inside the half grids part. And we found 42. So let's do the math here. So for 4, the correct answer, and we did like really look at the formula for 4, and we're pretty certain that we have the formula correct. We just haven't added those numbers. So it's really 2 times 1 plus 4 plus, and this is kind of, I think, just a coincidence for this case, 3 times the 3 by 3, so 60. Oh, not 3 times the 3 by 3 if we're only counting the first half. So that's my bad. So 10 plus 20. We should still be getting a much larger number than our program is giving us. But let's try to think about why here in a little bit. So 2 times 1 plus 4 plus half 3 by 3 plus 3 by 3. So half 3 by 3 is 10 because 3 by 3 is 20. 1 plus 4 plus 10 is 15, plus 20 is 35, times 2. It should be giving us a 70. It gave us 42. So clearly something in our math is not right. And so for the third run through, we started with 4. Or sorry, for the 4 by 4 grid, we started with 4. I and n both equal to 4, so of course we got that, and then n minus 1. 2 times n, that part's correct. And then what we expected is for I, when it equal 2, we actually wanted it to be here. But instead it went down here. So n of 4, I of 2. So our conditions are incorrect. So n minus 1 greater than or equal to 2, actually. So let's see if it went through the correct order. Now, again, looking at the 4 by 4 first. Okay, so went through the half grids part twice. I think we want, there's just less than instead of less than or equal. Checking it again. Okay, we got to 56 that time. And we're going through things in the correct order. So let's make these show us what we're adding. just always going to be 2. Okay. So it should be like 2 plus 8 plus 20, and then that should be 40. Probably should have just put the limit at 4. Let's say, so 2, 8, oh. Okay. So we should be looking up a 3, and instead we are looking up 2. Oh, pff. Gotta add my little curly braces if I want this to do the maths for me. Okay, so how can we make it do n minus I in the way that we expect it to do? So we want I let's see, thinking about this. So we come in here when I equals 2. And we want to look at limit to roots 3. And then the next time in, we would want to look, like, if for the 5, we would want to look at limit to roots of 4. Could it be as simple as, like, n minus I plus 1? Let's see how that goes. Okay. 70. Okay, well, I didn't change my documentation. That's my bad. So 2, 8, 20, 40. That is the correct answer. Let's see if we do for the 5x5 grid. Again, assuming this formula is correct, which I don't know if that's a fair assumption or not. We have our 2. Let's copy this down. And have our actual numbers here. So 1 plus 5 plus 10 plus 35 plus 70. So if our formula is correct, we should be getting 2, then 10, then 20, then 70, then 140. So 2, 10, 20, 70, 140. I can't promise that's the correct answer for reasons I think are obvious. But let's go ahead and throw a limit of 20 in here and just kind of see what happens. I am going to go ahead and comment out all of the print statements in here, because otherwise our output might be a little bit obnoxious. Let's leave this top one so that we can see it go through. And again, like, I think that if we did this, we could just start with an n, but we are building out our limit to roots so that we can look up these numbers and not recalculate things constantly. So let's go ahead and do limit of 20. It looks like this is relatively fast. If anything, all of those prints were slowing us down, but that doesn't mean it's going to be quite as fast for the number 20. Oops. Okay, never mind. Got real fast. Okay, so this is a much larger number than I was coming up with anything that I tried yesterday. If somebody comments and wants the video from yesterday, I am going to keep it, but I'm not going to upload it unless somebody asks for it, because it's honestly just over 3 hours of watching me struggle, and I don't think that's entertainment for anyone. But let's throw this giant number into Project Euler and see if we have found the answer. It's very exciting for me. Maybe. Nope. Okay. But I think we're a lot closer than at any point yesterday. Alright, so we don't quite have the correct number, but we have the correct number through 4. We're not sure about 5. It calculated the number that we wanted it to based on the formula that we came up with. I'm not 100% sure that formula is right, to be honest. Because I think that, like, this part is questionable. Because let's look at our 5x5 grid again. So here, if we go all the way, obviously that's trivial. If we go here, that's trivial. This is the part where we're kind of not sure. We come here, we know that's the 4x4. We come here, we know that's half the 4x4. But here, that's not the same as the 4x4. It's not really half the 3x3. This is half the 3x3, but there's a 1, and then there's... Hold on. 2, 3, 4, 5. So, can that be right? 1. Okay, I'm counting 2, 3, 4, 5. Okay. So if we go to the right here, it's 5. And if we come here, then that's half by 3. So I think... Okay, so this became a lot more complicated. What we're seeing here is, like, this is half of the 3x3 plus the original n. So if we add that into our formula, will it always be half 3 by 3 plus n is the real question here. Let's pull up a 6 by 6. Okay, so our trivial case, this is the one where it gets confusing. Obviously, if we come all the way down here, that's half the 3 by 3. If we come here, then it's basically the 1, 2, 3, 4, 5, 6. And when we come down here, then it's the 1, 2, 3, 4, 5. And then here is the half by 3 by 3. So it's like n, then n minus 1. And I'm willing to bet that it kind of works the same for the 4 by 4 part. So like this one, we know this is the 5 by 5 at that point. It's just the 5 by 5, no questions. This is the half the 5 by 5. This, if we come down to here, is half the 4 by 4. But if we come up here, we've got our this one, and then we've got this one, and all of these paths. And then we have over here where then we also still have the paths for like our 2 by 8, or our 2 by 4, excuse me. So I think we are going to need a little bit more complexity in how we size up these grids. So I'm gonna go ahead and assume that yeah, lost my train of thought. I'm going to look at them always as like smaller x, larger y. And then we just multiply by 2 to get the correct number of roots for the other side. So like rectangles. So our 1 by 2 would be coming over here. Realistically, we're not going to look at the 1 by 2, but like just kind of start thinking about it. 1 by 2 would be, say, half this rectangle, or half this square specifically. So like ignore half the square. If we start here, then there's 1 and 2 and 3 ways down. So 1 by 2 is equal to half of the 2, which is 3. And I am once again going to start with the comment. 1 by 2 is equal to 1/2 of the... Okay. Fingers are not cooperating. 2 by 3 is equal to 1/2 of a 3 by 3. 3 by 4 is equal to 1/2 of a 4 by 4. So let's kind of think about the extension of that pattern, right? So that pattern becomes n minus 1 times n grid is a 1/2 of n by n. Now, what about an n minus 2 times n grid? So this would be like 2 by 4. Think about how our 2 by 4 will look. So it'd be this section of the grid. Let's actually just look for a 2 by 4 grid. Why make our lives harder than they need to be, right? Okay. I expected it to be the other direction, but doesn't matter now. So obviously if we do the same thing that we normally do, where we like go to the 2 by 2, so 6, what if we come here, then 1, 2, 3 different ways to go, plus 1. So 1 plus 3. We're at a 2 by 3 effectively. I'm confusing myself by having it the wrong direction, frankly. Okay, well... let's go back to the one that was at least the right size. Okay, so we've got 6 if we go all the way there. We come here. There's the 3 different ways plus 1. We come here. Then there's 1, 2, 3, 4, 5 different ways. So 5 plus 4 plus 6. So 2 by 4 equals the 2 by 2 plus 5 plus 4. Some of that is an artifact of it being just 2. And that is equal to 15. So let's look at a different n by 2, or n minus 2 times n. Because based on this sample size of 1, the formula would look something like 2 by 2 plus n plus 1 plus n. Or to put it more simply, 2n plus 1. 3 by 5 is, obviously there's 3 by 3 in there. We can just kind of eliminate that. again. Obviously, we come down to here. We get our 3 by 3. Come only down to here. Then we have a 3 by 4, which is half of a 4 by 4. So there might be a little bit of a trick here. I think that it's so I think it's like half. That was a 3. I did not mean to type a 3. N minus 1 by n plus n. Let's see if I'm right here. So if a 3 by 5 is equal to a 4, half of a 4 by 5 plus 5. So this would be 1/2 4 by 5 plus 5. Half of a 4 by 5. We know is half of a 5 by 5. I think for 5 by 5 we may not have found the correct answer. So we don't actually know for sure. But this looks correct to me. Let's go kind of just look at it. So this one, because this is like oriented to the top here, if we go all the way over here, no, we can do it this way. This is fine. So obviously this is our 1. Go here. And this is our one. 1, 2, 3, 4, 5. And we come here, and that's a 2 by 4. So 1, 2, 3, 4, 5, 6 total. Come here, we're in our 2 by 4, which we calculated. So as 15, so 6 plus 15 plus, this is actually a 3 by 4. Or 6 plus 15 plus what's a 4 by 4? $70. Which is 35 plus 15 is 50, so 56. So 3 by 5 being 56. So it's not really 1/2 of a 4 by 5. Think about this. So 3 by 4. So n minus 2 by n, 3 by 5, would be the same as n minus 2 by n minus 1 plus n minus 3 by n minus 1 plus n. So this is some stuff here, huh? Let's try to represent our formula in a different way. Like, just kind of thinking through things a slightly different way. What's our actual formula? So, if we think about it in terms of going all the way to the right or only certain amounts to the right, and then counting how many paths when you start going down. Obviously, it's going to be 2 times. The 1, I think we should keep as just a 1. 2 times 1 plus n for the only going that far. Going all the way but 1. And then it's n minus 2 by n. So for 2, because it's this special case where it's just that, we can ignore this part. So then it would be n minus 3 by n. So like in our 3 by 3, we'd ignore this part. But we basically get down to n minus n minus 1 by n. So n minus n by 1 is just 1. But we don't really want to do 1 by n. What we want to do is let's pull back up our 5 by 5 just for purposes of thinking things through. Okay, so this is our 1, this is our n, this is our 2 by n, 3 by n, 4 by n. Except that's not really the right way to think about it, is it? Because this is our 1, this is our n, and we're not going this way. So we're ignoring this path. And the same thing for here. We're ignoring this path, so it's really a 2 by 4 that we're analyzing for the going all but 2 to the right. So it's n minus 2 by n minus 1. So like for 5, it would be 1 plus 5 plus 2 by 4 plus 3 by 4 plus 4 by 4. Okay. I am a lot more confident that that's the correct answer. So 2 by n minus 1 plus 3 by n minus 1 until we get to n minus 1 by n minus 1. So for 5, 4 by 4 is it 70? I think it's 70. Should have written that down, shouldn't I have? Yeah, it's 70. Because it's the 35 times 2. So, which equals 2 times, let's merge these together, 6 plus a 2 by 4 is 15, plus a 3 by 4 is 1/2 of a 4 by 4, so 1/2 of 70. Which is 1/2 of 70 is 70 plus 35 is 105. 105 plus 15 is 120, 126. That should be an equal sign. So 126. And that is... Did I multiply by 2? No. So 6 times 2 is 12, 2 times 2 is 4, so 252. So in our count here, we're missing 10. So, how do we write out this formula? More specifically, how do we write out this formula for a 20 by 20. And actually do that maths. Okay. Can we express any of these other terms, say, in terms of each other? So, like, n minus 1 by n minus 1, n minus 2 by n minus 1 is 1/2 of this. So, like, I kind of snuck that in there. N minus 3 by n minus 1 is the same as n minus 2 by n. Is this the correct formula for n minus 2 by n? I'm not sure. Okay, but I think we're pretty close here. The hard part about this is to find the number of routes for any grid size. You need to know the number of routes for all grid sizes that are smaller. That's not easy to calculate, as we've seen. Let's see. So, let's make this like tuples. A grid of size 1 has 2 roots. A grid of size 2 by 2 has 6. 3 has 20. I'm not gonna start adding 4 because that's a good test case. A 1 by 2 would have 3 because it is half of a 2 by 2. Actually, maybe that's it in general. By n equals n plus 1. Yeah, that's correct. So 2, 3 is 1/2 of 3, 3, so 10. Can we generalize a 2 by n? It's tricky, right? Because a 2 by n is not Like in the case of 2, 3, it's trivial because it's just half of 3, 3. But for 2, 4, it would be like our 2, 4 here. It's 1, 2, 3, 4, 5. So it's the... Oh, that's it. For 2 by 4, it's 1 plus 4 plus 2. 1 by 4 plus 2 by 3. So for 2 times n, it is the same as 1xn plus 2xn minus 1. Okay, so we're getting close here. Obviously, this is going to be my longest video, no matter what I do. 3 by n is... Okay, so thinking about, like, this 3 by 5 here. 1... So it's like a 1 by 5 plus a 2 by 5 plus a 3 by 4. So 1 by n plus 2 by n plus 3 by n minus 1. And I think this is our pattern. This is... I know I say that a lot, but I mean it this time. And again, this only works where n is greater than 3. 4 by n, where n is greater than 4, is going to be the same as a 1 by n plus a 2 by n plus a 3 by n plus a 4 by n minus 1. Right? Let's double check ourselves. So 4 by 5. That's our 1 by 5. Ooh, but it's not quite, is it? Because this is counting it as a duplicate, because it's counting this again. Dang it. It was too easy. Let's see, so here, what this actually is a 4 by 5 plus a 4 by 5. Oh. Can that help us? N by n equals 2 times n minus 1 by n. That is... tricky, isn't it? So this is not correct. And I'm just gonna go ahead and delete this. But n by n is equal to 2 times n minus 1 by n. N minus 1 by n. Well, I guess we did already know that, but we're thinking about it from the other way now. N minus 1 by n. Can we express that in terms of something else? So basically, trying to figure out how can we get down to... How can we make up a formula where we basically just do math? So we can have an algorithm that just works and doesn't loop forever. So n minus 1 times n in terms of smaller. So let's think about this in terms of downs first instead of overs first. So obviously if you go down 1, you get the n minus 1 by n minus 1. So it is really then n minus 1 by n minus 1 plus n minus 1 by n. So n minus 1 by n equals n minus 1 by n minus 1 plus n minus 2 by n. How does this help us? Not quite sure yet. But we're getting closer, I feel like. So now, alright, we're looking at... Let's look at the n minus 2 times n, because I think that's the more confusing one. Because this, it's like... That's another n by n, realistically. But the n minus 2 by n, that's a 2 by something. So we really need the formula for a 2 by n. And let's again, for a 1 by whatever, the number of routes is n plus 1. So 1 x n, these should all have spaces, is n plus 1. Okay? So if we think about like a 2xn, what is that? So 2 by 5 is equal to a 1 by 5 plus a 2 by 4. Plus 2 by n minus 1. Okay. Let's think about a 3 by n. So 3 by 5 is equal to 2 by 5 plus 3 by 4. So 2 by n plus 3 by n minus 1. And then dot 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 is in between here. So every grid of every size, we can represent these paths, these lattice paths, in terms of the two grids that are made up by deleting that upper right square. So like for a 2x2, we can look at it as two 1x2s. For a 5x5, let's think about rectangles instead of squares. For a 4x5, it's a 3x5 plus a 4x4. For a 3x5, it's 2x5 plus a 3x4. And then for a 3x4, it's 2x4 plus 3x3. So every single one of these grids can be expressed by the two inner grids that are like, ignore this guy and reuse the middle squares. And I think that that is the actual key. So the thing is that when the ends are equal, it's just two of the smaller square. So 4 by n is a 3 by n plus I lost it. A 4 by n is a 3 by n plus a 4 by 4. Or more accurately, a 4 by n minus 1. So let's think about this in terms of n equal to let's write it out in terms of like 6 by 6. So 6 by 6. That equals 2 times 1 plus n plus a2 by 5 plus a3 by 5 plus a 4 by 5 plus a 5 by 5. And 7 would be the same, except the 5s would be 6s. So 2 times 1 plus n plus 2 by n minus 1 plus 3 by n minus 1, etc. n minus 1 by n minus 1, which I think is pretty similar to a formula we created earlier. Did I not express it in terms of n? Okay, so half of 3 by 3, which is not really correct. Yeah, this is... the end of the series was the same, but the beginning wasn't thinking about it quite right. So... what we can see here is the number of terms in this series is... so, like, the number of terms in the series part of the series, the total number of terms is going to be, like... so for the case of 20, n minus 1 is 19, 2 to 19 inclusive is going to be 18 numbers. So it's going to have the same number of terms as the same number of terms as the one prior. So, like, if we kind of think about how we would go about finding all of these terms, right? It's... is this actually 19 terms? Hold on. This is actually 19 terms, because that n plus 1 is just 1 by n. Okay. So, count roots. Let's take in a num. Actually, just take in an n, it's fine. I think we reuse that variable name elsewhere, but we're probably going to be deleting some code. So, it does not matter. Okay, so, count roots. We come in with an n. In fact, let's do xy. So if x is equal to y, then we want to return 2 times oh dang. I may have just cracked the case. 2 times count routes x minus 1, y minus 1. Is that correct? No. N minus 1 by n. So it's not really this twice. Okay, so first of all, now let's do if x equals y. Or if x greater than or equal to 1 and x equals y. Let's see, if x equals 0 or y equals 0, we just want to return 0 in that case. We've gone too far. Or possibly 1. Okay, so thinking about this. So if x equals y, let's say that's 2 by 2. Let's say we threw 2 by 2 in here. X equals y, we want to return 2 times 1, 2. So when we come in with a 1, 2, that is a 1 by n, which is just n plus 1. So if x equals to 1, return y plus 1. And then otherwise, x is going to be some number smaller than y, which means it's going to equal count routes of x minus 1 y plus x y minus 1. I feel like I very much have tried this before and not had it work the way that I want it to. But just for the sake of things. Okay, so we have this formula that we're pretty confident does actually work, but like it does not matter because it takes too long to run. Okay, so let's put our limit back to 2. Let's add a print statement to the end of this. And let's see if we have created an infinite loop by accident. So we want to print count roots for limit. That's an encouraging sign, isn't it? Let's try 4. That's also correct. That's also the number we calculated for 5 by 5. Maybe we got it? Maybe. Okay, 20 takes longer. Makes sense. 20 is bigger. it occurs to me that I should flip these two. Should be like that. I don't know if that'll make us a little bit more efficient or anything, but... Okay, I am very impatient right this second. I just want to see it doing things, right? Ooh. Yeah, so it's looking for 2x2 repeatedly. Not a good sign. Let's go ahead and build in a special case just for 2x2. If x equals 2 and y equals 2, return 6. Kind of cheating for the smallest of cases, but let's see how well that turns out for us here. Okay, so something's wrong where it gets stuck looking for these numbers. So it's looking for all these little numbers repeatedly. Let's kind of create a little cache going on here. Come back with our num routes, and we are going to do this. We're going to start with this guy. I'm actually going to delete these first two so that we can keep our special formula for x equals 1. So if x, y in num roots, you want to return num roots for xy. And then for these other cases, we want to actually record our, value. So, num roots, forget our tuple, equals value, return value. Same thing. So we're not gonna putting anything where it's like a 0 or a 1. let's see if that breaks us out of infinite looping. It did. And it gave us a different and larger number. Oh. I want to print num roots. I want to see how huge that got. Okay, so our 2, 2 is 6, our 2, 3 is 10, blah, 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 blah. All of this jazz. Okay. One more time. Let's see if this is the correct answer. I have checked the answer so many times that Project Euler is like, you sure you're not a bot, though? Goodness. That did it! Okay, so that problem took almost 5.5 hours total. But done. So the trick was, in this case, just noticing that singular pattern of all of these grids are composed of these two smaller grids, and you just add those together. And yeah. Let's delete some stuff that doesn't make sense to keep. So, n by n, this is the correct formula. This doesn't really help us. I think this stuff was kind of helpful, but like, took me ultimately down the wrong path. I want to leave these notes. No, I don't. There's so many here. Okay. So this is what really got me to the right conclusion, was thinking about it in terms of this. So n by n is 2 of n minus 1 by n. N minus 1 by n is this. Let's grab all of these. So we can kind of see how it's like n plus 1. Yeah. And then adding in that cache really made it so that we actually started getting answers instead of looking up the same thing repeatedly. And let's just go ahead and delete all of this stuff that didn't work at all. How about that? Cool. Now this file is actually kind of more readable. So, review. Took forever, but figured out the formula. The formula is this, at least for the larger numbers. It is 2 times n minus 1 by n, and n minus 1 by n can also be expressed in terms of n as this. And if you think about it all the way down to 1 by n, that's just n plus 1. 1 by n plus 2 by n minus 1 is 2 by n, which is part of 3 by n, which is part of 4 by n, so you just come up, eventually, it's just this formula. And in order to implement that formula and have it be variable, I wrote this recursive function. Some compilers or some linters prefer a double space there, so I'm trying to be in that habit. Should set my linter up to do that for me. So, if I come in with two numbers, x, y, this is probably n by, so starting with n by n. And we have a little failsafe here. It should never reach this point. but we do have a little fail-safe to be like, hey, do we get all the way to 0 somehow? Because that's wrong. That should not happen. And I actually think that we shouldn't have anything. This dictionary is printed out in a way that's kind of hard to read. But I think that we don't have anything where it actually get to a y lower than x. I'm obviously just spot checking, but it looks like it's all x, y, and y is smaller, if anything. And then if x is equal to 1, then we know that's y plus 1, because that's like our 1 by n case. If we've already calculated this combination, let's just not calculate it again. Just in case. It might be hard, it might be large. Calculations. Make our lives a little more efficient, please. And this print statement isn't really necessary, but it makes me feel better. And so when we have an n by n case, then we know that it's 2 times n minus 1 by n. We call it again. Then finally we calculate the value by looking at x minus 1 y and x y minus 1 added together to recognize that, like, it's these, we're basically calculating two different rectangles. And of course we're saving those values in our little, I'm going to call it a cache, it's actually a dictionary, but it caches our values for us. And then when we finally just return this answer, and when it goes down and comes back up, we finally get the correct answer of, in this case, this number that I'm not really going to try to read, frankly. So yeah, it went all the way down to 4 by 4. But it didn't go down to 3 by 3 because that's already in numbers. We could not have anything but 2 by 2, I think, and still have it work. But, or possibly nothing at all. Let's real quick just try it without having num routes initialized with anything. I think that will cause some issues. But let's... Okay, it looks like that's the correct... That's the same number. And that time it did go all the way down to 2 by 2. And 2 by 2 would be 1 by 2, which would be x equals 1. So there we go. I think that's the same number. Yeah. Okay, so cool. Done. I hope that made sense to someone. I am sure that if some math expert watches this, they'll be like, you should have seen that formula sooner, and you're not wrong. But I was trying to do it all by myself. I was trying not to look up the answer to the actual problem, if that makes sense. So I'm fine looking up, like, how I make Python dictionary do X or whatever. But when it comes to actually looking up, how do I solve this exact problem, that feels like cheating for the purposes of Project Euler. But in any case, let's oops. delete it instead of cutting it. Actually, let's just comment out our print statements, except for the exact answer, or I suppose that doesn't really make a difference. So it's 0037.4, and we started at 0037.39. So literally, like, basically no time at all here. It performed effectively, I think, 20 or possibly 400 equations, because we come in x equals to y, so we're looking for the 20 by 20. So we look at 1920. 1920 comes to here and looks for both 1820 and 1919. 1919 comes here and looks for 1819, which looks for like 1719 and or 1819 would look for 1719 and 1818. So it just effectively it just goes down to calculating this. And then it just multiplies it by 2 or adds 2 results together. And I'm pretty satisfied with that. I'm going to stop rambling, and I'll see you in the next one.